All right, so notice that the magnetic field is going to cause a deflection of the charges. Okay, so that's one way of using it. So the next question is, let's talk about the magnetic propulsion.
The ride's propulsion system is a simple yet complicated mechanism. A series of electromagnets, called stators, line the horizontal portion of the track. As the magnets beneath the car pass over a stator, it is energized, first to attract and then to repel the vehicle.
All right, so the propulsion works straightforward, but this time we have to focus on the details. So the light poles will repel, non-light poles will attract. They have permanent magnets right under the train, so this is always going to be the north pole, this is always going to be the south pole, this is the alignment of the magnets. On the tracks, you have magnets whose polarity you can change. So the question is, how do you end up changing the polarity of the magnets on the tracks? All right, just guys, imagine that this is your magnet. Also imagine that this is about 6 feet in length, and put them on rotatable tracks. And then you have to get a bunch of illegal workers from Canada and give them headsets. And then say, hey, George, just spin yours, and then Mark, it's your turn, and then synchronize them, all right? That you can do with Canadians because they got free healthcare, all right? So, and then once you can get them to synchronize, obviously you can change the polarity of these magnets at will. But except, you know, you got to synchronize it within a fraction of a second. So no Canadian could do that, as far as I know. So how do we change the polarity of the magnets on the tracks? The way we change the polarity of these magnets on the tracks became possible because of this guy. His name is Oersted. I want you to remember this name because this is a crucial name. What's his name? Oersted. Can you guys remember this name? There's no Einstein. His name is Oersted. All right, so Oersted is an important name because of Oersted, we have a lot of the technology that we have today. Also, it's an important name because of the simple reason that, for one of the reasons, guys, if you find yourself in Europe, if you get confused, you could get yourself beaten up pretty badly. All right? People tend to be very sensitive about their nationalities and their cultures. This guy is Danish. All right. So you're thinking Danish, does this mean that he's edible? No, we're not talking about pastry. So don't confuse Danish with pastry. That's number one. Number two, if someone is Danish, what country would they be from? All right. Is he from Finland, for example? If you're thinking yes, I would say stay in the United States. Don't leave the United States unless you're taken hostage or something. Okay. Don't fucking go to Europe because somebody's gonna get really offended. All right. So if he's Danish, he's obviously from what country? Ian says Denmark. 5 points for that. Not Finland. All right. If somebody's Danish, they're not from Finland. All right. If someone is Finnish, then they're from Finland. Just remember that. So this guy is Danish, and the reason why it's important is because you will see his picture in their Danish currency. All right. So they really value this guy, and you will see his statues all over the place. Europeans being very culture-minded, the science is really, really important. So what did he discover? This guy is, I think he was a high school physics teacher, more than likely, and he's lecturing. Year is supposed to be 1819 or 1820. Okay, guys, it's like 200 years ago. Physics lecture. Imagine. Probably it was really exciting and hot because he probably had amazing PowerPoints. Anyway, so he's trying to demonstrate the fact that when you run a current for a wire, it heats up. That's a hot lecture right there. So the students would just line up, and he had this basic battery. He would run a current through it, and then he would stop the current. The student would go up to the wire and get this warm and fuzzy feeling, and then the next student would experience the same thing, and blah, blah, blah. So as he was doing this small demonstration, he noticed that when there was current in the wire, there was a deflection in the compass because there was a compass sitting nearby. And all of a sudden, he puts two and two together to realize that what causes magnetism is the current inside the wire.
Hans Christian Ørsted discovered that electric currents produce magnetic forces.
So what caused magnetism? Electricity, that's it. And how was it discovered? Just by chance. Okay, so welcome to my part of reality. A lot of good physics is discovered by chance, all right? Today, we force ourselves to discover something, and we go nowhere.
And
that's it. So current runs through
forces
it.
Always make magnets point perpendicular to the direction of the current.
And this was exciting. All right, so what do we know? The current generates magnetism. And you can trace the magnetic field using a compass, that's it. And then we will get to use our right-hand rule one more time to figure out the direction of the magnetic field, if you know the direction of the current. All right, so we got two right-hand rules. So the first one is the right-hand rule number 1. The second one is going to become the right-hand rule number 2. How does that work? Well, so what you need to do is line up your thumb in the direction of the current. The current is going in the opposite direction. And your fingers will curl in the direction of the magnetic field. And then we will gently call this the right-hand rule number 2. All right, so first step is the guy who discovers that the current causes magnetism. All right, so the current is going in the opposite direction. Okay, let's wait. I is going to be our current, and the magnetic field is going to wrap itself around the current wire. All right, two-dimensionally, the magnetic field is coming out of the page, and it's going into the page. Three-dimensionally, it's going to look like this. All right. This is your magnetic field. That's it. All right, so line up your thumb in the direction of the current, and your fingers will curl in the direction of the magnetic field. And this is our right-hand rule, number 2. And this is what Ørsted discovers. I think I'm just going to make it 1820. It could be 1819, so I don't care. It was a long time ago. Just a chance discovery. And so the current causes magnetism. Applications. All right, so the current is coming out of the page. And the current is going into the page. If the current is coming out of the page, all right, cool, this worked. All right, if the current is coming out of the page, so, all right, guys, this current is coming out of the page. Okay, this is white against the white. If it's coming out of the page, line up your thumb in the direction of the current. Your fingers will curl in the direction of the magnetic field. So it's curling in that direction. So if you reverse the direction of the current, let's check to see if we can make a one full circle. We did, it worked out. All right, so if you reverse the direction of the current, the magnetic field is going to reverse direction as well. That's it. So what could we do with this, which is really, really neat? Okay. What we could do with this, which is really, really neat, was discovered by someone named Henry. I think that's his last name. He was a high school physics teacher in Rochester, New York. All right, and as he was goofing around, he discovered the following. All right, so he noticed that if you run a current, this is your current wire. If you run a current through it, obviously the current is going to generate a magnetic field. And it generates a magnetic field going in this direction. Okay. And then he noticed that instead of using a single loop, you can just wind it up, introduce more and more loops. All right, so just turn it into a coil of some sort, just like that. And all of a sudden, he was able to intensify the strength of the magnetic field. So, which means that now it's going to look like this. You notice that by using loops like that, you could generate an electromagnet. Now this becomes a magnet that you're looking at. And then he noticed also that if you place an iron core in the metal, iron is very easily magnetizable. Now this becomes the north pole of it, and this becomes the south pole of it. This turns into an electromagnet under the circumstances. All right, so the current is moving in this direction. Likewise, if you reverse the direction of the current, you end up reversing the direction of the magnetic field. All right, boom, now the magnetic field is facing the other way. And once again, if you were to place an iron core in the metal, what happens to iron? This becomes magnetizable. And it was able to change the polarity of the magnet. Okay, guys, these are known as electromagnets. The guy who discovered it, once again, he was a high school physics teacher. Henry, Rochester, New York. And so the electromagnet was discovered here in the United States, roughly about 200 years ago. And we got the solution to our problem. Solution to our problem is, okay, so pick out the best answer first. Whenever you're ready. Yeah, I mean, the current is coming out of the page, so it's going to curl in the counterclockwise direction. So give yourself 5 points. Those of you guys who like A, give yourself 2 points. All right, so these are your electromagnets, guys. All right, so the current is going to just magnetize the iron core in the metal. If you reverse the direction of the current, you're going to end up changing the direction of the magnetic field. Okay, so on the tracks, what do you have? You've got these electromagnets. Okay, depending upon where the permanent magnets are, under the train, okay, so everything is computerized, you can just reverse the direction of the current for the magnets on the tracks. And as soon as you reverse the direction of the current, it reverses the polarity of the magnet. All right, so that's how this works. So, all right, guys, we'll continue tomorrow. Okay, so do the participation quiz. And then if you have any questions, just stick around. I'll be back in 10 minutes. Okay, guys, let's get moving. Quick review. All right, so the magnets, they have 2 poles, north and south. So where do we get this nomenclature from? Where do we get the terminology from? Why is it that one side is called the north pole, the other side is called the south pole?
From the Earth.
All right, guys, jump in anytime you feel ready. And before you jump in, let me unmute everything. All right, so the computer's on. So where do we get the nomenclature from?
Bert,
All right, explain more. And just try to use this complete sentence this time.
this is an English class
No, it's not, but we got to communicate somehow.
because the North Pole is attracted to the north end of our planet.
Okay, so the North Pole of a magnet, if it's suspended through a string or something, it's pointing towards the North Pole, right? That's the reason. All right, so they noticed that the magnetic field lines start at the North Pole of a magnet right here, and then it South Pole of a magnet. Okay, how do you know that? Okay, so where do we get that idea from?
We can measure the field with a compass.
All right, you can map the field using a compass, right?
Right.
So you can. That's what we do, guys. If it's visual, obviously we can visualize it. We can map something. Okay, that's how we know that the electric field lines come out of a positive charge point towards a negative charge. A lot of what you see is a lot of what we can actually map. All right, so how does the magnetic field affect the charge at rest? If the charge is at rest, what happens? The magnetic field is gonna do nothing. If the charge is moving parallel to the magnetic field, again, nothing happens. Welcome to your lives. Anyway, so if it's going across the magnetic field, what happens? Charge is going to become deflected by a force perpendicular to its motion, right? And Ian was pointing out that it's also perpendicular to the magnetic field. That's fine. I'm more interested in the force being perpendicular to the motion, because if it's perpendicular to the motion, it just causes circular motion. So that's the reason why I kind of focus on that more than anything else. All right.
I was just from your diagram, I couldn't tell what that was supposed to be.
It's modern art. Anyway, so moving forward, you don't need to, as long as you feel something when you look at it. All right, so moving forward, right-hand rule number 1 is not the right-hand rule number 2. All right, so you're looking at it, right? So line up your thumb in the direction of the velocity vector, fingers along the direction of the magnetic field, and your palm is gonna face in the direction of the force field. All right, so what purpose does the right-hand rule number 1 serve? All right, jump in anytime you need points, so I don't care, or else I'm just gonna run through everything. All right, so the purpose of the right-hand rule number 1 is to figure out the direction of the force of deflection. So that's the purpose that it serves. Okay, question number 8. Obviously, we skipped this one. So what do we know? Positive charge moves from top of the page to the bottom, so it's moving in this direction. And the magnetic field is from left to right. So using the right-hand rule, thumb is going to be in this direction, the fingers are going to be in that direction. So your palm is going to point, it's going to face out of the page. So the magnetic force will be pointing out of the page. So that's what we got. All right, question number 9. Did we do this? If the current moves in the upward direction within a straight wire out of this page, so the current is coming out of this page. So if the current is coming out of this page, then what happens?
You get counterclockwise.
Yeah, it's going to be a counterclockwise, right? So that the current is coming out of the page. If that's the case, using the right-hand rule number 2, this is going to be counterclockwise direction. That's the direction of the magnetic field. All right, so how does the Earth's magnetic field protect us from charged particles from space? So what happens to the charged particles coming from space? When they cross the magnetic field, they will get deflected around the magnetic field. Eventually, they will be driven into the atmosphere, causing the southern as well as the northern lights. All right, magnetohydrodynamic propulsion unit, we discussed that. That's an application of the right-hand rule number 1. I don't want to get into it. The formula regarding the magnetic force acting on a charged particle, we'll get into it. We haven't covered that. Okay, 14, we didn't do that. Okay, what else did we do? All right, so move on to 30. So what did Ørsted discover? Ørsted discovered that the current causes magnetism. That's it. So he discovers that the current causes magnetism. All right. So this is going to give us the right-hand rule number 2. So the right-hand rule number 2 is exactly this. All right, line up your thumb in the direction of the current. Your fingers will curl in the direction of the magnetic field lines. All right, so we discussed this earlier. So the current is coming out of the page. So the magnetic field is going to wrap around in the counterclockwise direction. If the current is going into the page, it's going to wrap around. It's going to curl in the clockwise direction. All right, so what else do we have? Forget the formulas. We didn't discuss anything mathematical. All right. Okay, so evidently we've been jumping around. All right, the last thing that we did was the electromagnet. How does it work? All right, so the current is going to cause the current loop, more like it. The current is going this way, so it's going to cause a circulating magnetic field around it. So by increasing the number of turns on the loop, okay, you can turn this into an electromagnet. They end up placing a by placing an iron core in the metal, they can intensify the strength of the magnetic field. Iron is very easily magnetizable. So the question is why? Why is that iron is very easily magnetizable? So is nickel.